Okay, welcome everyone to HAO Colloquium today. And our today's speaker is Haruhisa Izima-san from Japan, Nagoya University Institute for Space, Earth Environmental Research. Haruhisa Izima is an associate professor at the Center for Integrated Data Science, Institute for Space, Earth Environmental Research, Nagoya University. He received his PhD in Earth and Planetary Science from the University of Tokyo in 2016, where he developed numerical codes for radiative magnetohydrodynamic simulations to study solar chromospheric jets. His research interests include solar physics, computational physics, and space weather, with a particular focus on solar wind formation, coronal heating, solar cycle predictions, and numerical techniques for magnetohydrodynamic simulations. Today, Haruhisa Izima-san will be talking on probing the sun's small-scale dynamo through solar wind diversity. To Izima-san.
Hi. So can I start now?
Yes.
Oh, okay, thank you. Thank you very much for giving me a time to talk about my research today. And I'm sorry I could not attend in person. My talk is on the numerical simulation of the solar wind, especially focusing on the physical connection between the solar wind formation and the small-scale magnetic structures on the solar surface. My collaborators is the Takuma Matsumoto, Hideyuki Hota in the same institute, and Shinsuke Imada in the University of Tokyo, and Daiko Shiota in the NICT in Japan. So let me start. The physical origin of the solar corona and the supersonic solar wind has been a challenging problem in the solar physics. This problem is, in other words, to quantitatively understand the generation, transport, and the dissipation of magnetic and plasma energies from the solar surface into the corona and into the solar wind. And this, to understanding this energy process very quantitatively is important for solving this problem. This energy transport process is important not only for the sun, but also for the Earth's surrounding a high latitude atmosphere around the sun. For example, from the visible surface on the sun, visible light comes to the Earth and heat our planet. And from the corona, we have ultraviolet or X-rays, and it ionizes the higher Earth's atmosphere. And from the solar wind hits the Earth's magnetosphere and deform its shape and determine the geospace environment near the Earth. And the important part is that a very small portion of the energy is used for the coronal heating and the solar wind acceleration. For example, the solar visible energy flux or total energy flux is about 1,370 watt per square meter near the Earth. But only 0.01% of this energy is used to hit the solar corona, and only a fraction of this coronal heating energy is used to accelerate the solar wind. Thus, it is very important to, especially for modeling, it is important to model these energy transport process and dissipation process in a quantitative way. And my today's talk is on the relation between the solar photosphere and the solar wind. We found that the solar wind is more closely related to near-surface magnetic convection on the sun than we have expected before. Before going to that topic, let me review our theoretical models of the solar wind formations. The first theoretical model, famous theoretical model, is the gas pressure gradient force model, suggested by Parker, 1958, before the discovery of the solar wind by satellites. And the height of the energy input closely is very important, especially for the fast solar wind. I will explain about this later in this talk. And in order to input the energy in the higher layer of the solar atmosphere, the alpha wave is a very important energy carrier. And the incompressible alpha wave turbulence models have been suggested as a framework to model the solar wind formation. And these processes are sometimes implemented in the global models, and sometimes used for the, for example, the space weather predictions. And below this line, currently it is very rare for used in the solar wind prediction. The shock waves and the decay instability is an important process. This is, in other words, compressibility of the MHD waves are important, as it provides additional dissipation process in the solar wind. Because the alpha wave is very difficult to dissipate in the higher layer of the atmosphere, this compressible process helps to dissipate at a certain height of the solar wind, so that the solar wind becomes a bit realistic. And also the roles of the magnetic reconnection is also an important factor. Magnetic reconnection has been related to the solar wind formation, at least since the 1990s, and maybe from before this era. And thanks to the Parker Solar recent satellite observations by the Parker Solar probes and the solar orbiters, we have many observations which indicate a close relationship between the magnetic reconnection and the solar winds. And there are many studies on the relation between the magnetic reconnection and solar wind, and then the spatial scale starts from the ranges from the 10 megameter into the global scales. But the difficulty on modeling the energy driver, modeling the solar wind formation, is the energy driver or energy input into the solar atmosphere. It is because the sun's magnetic field is very complex. This movie showed the evolution of the photospheric magnetic field on the sun. And this is only a portion of the whole global sun. And the global structure of the magnetic field is also very complex. And these processes are very complex to parameterize. And but the problem of the coronal heating and the solar wind acceleration requires a strong, a very high accuracy quantification. And quantification is very important because there are multiple processes has been suggested as a formation process of the solar wind or coronal heatings. For example, the one famous categorization is the impulsive energy release by magnetic reconnection and the steady energy release by the turbulence, and which is important. So we decided to simulate the magnetic convection on the solar surface in a semi-numerical box so that the energy input becomes very realistic. The numerical simulation of the solar photosphere has been already established. It is a very successful numerical simulation model, which is pioneered by the Rob Stein and A.K. Nordland around 1980 and 1990. And recently, this model is extended for simulating the solar chromosphere, corona, and solar wind, introduced in this talk. By solving the near surface convection or magnetic convection in the upper layer in the same numerical box, we can mimic the wave dynamo actions in the solar convection zone and wave excitation excited by the interaction between the magnetic field and thermal convection, and the energy transport into the higher atmosphere and the dissipation in a same numerical box. So these models are self-consistent, and we need no empirical heating terms or turbulent closures to hit the solar corona or accelerate the solar wind. And we have also developed this kind of code, which is called RAMENS, radiative magnetohydrodynamic extensive numerical solver. And the basic equations are the compressive MHD and radiative transfer equations, and the non-ideal equation of states and opacity, and stiff anisotropic thermal conduction along the magnetic field lines. But the most important, most unique point of our code is that we can simulate in an orthogonal curvilinear coordinate. This enables us to simulate the solar atmosphere along the magnetic flux tube, expanding magnetic flux tube, like the right figure, from the upper convection zone into the higher layer of the solar atmosphere. Because the horizontal size of the numerical box is very limited, typically at least 10 times smaller than the solar radius. So we need to simulate in a very local simulation box. So it is this orthogonal curvilinear coordinate is very important to simulate the solar wind by accounting the global expansion of the magnetic field. And this is one example, the sunspot bipolar sunspot simulations. Near the center, we have sunspot structures and many tiny convection patterns surround these sunspots. And this kind of simulation can be done in our code. And the drawback or disadvantage of the relative immunity simulations of the solar atmosphere is its computational cost. Because we need to cover the high density ratio from the photosphere into the solar wind, the density ratio exceeds 10 to 15. So we need many numerical grid points in the along the vertical axis. And also the temporal and spatial scale is very different between the photosphere and the solar wind. And we need large supercomputers. In this study, we used the Fugaku supercomputer in RIKEN RCCS. The typical computational resource introduced in this today's talk is about a week with 35,000 CPU cores per case. And this is our first comprehensive simulation of the solar wind and the upper convection zone. This is published as Age Metal 2023 in APJL. The left two panels show the vertical slice of the solar wind speed and the radial magnetic field. We found that the very intermittent solar wind structure emerges in the numerical simulation. And the right panels show the fractal observation at the point of 29 solar radii from the solar center, or 28 solar radii above the solar surface in the numerical box. The solid line shows the single point observation, and the gray shaded region shows the max and minimum range on the horizontal plane at the same height. The top panel shows the higher variability, and the wind densities also varies in time greatly. And we also found that sometimes we have a reversal of the radial magnetic field, which recently attracted attentions by the rediscovery by the Parker Solar Probe, also known as the magnetic switchbacks. The right bottom two panels show the measure of the X-ray intensity, more exactly the differential emission measure at the 1 million Kelvin, and the photospheric magnetic field. And we have a transient brightening in the corona, and also the structured coronal lobes, and which is produced by the dynamo-generated magnetic structures, which is self-consistently generated in the semi-numerical box. And we checked the magnetic field strength in the photosphere and the differential emission measure in the solar corona, and the rate of the switchbacks, and the speed of the solar winds and the mass loss. And we think that this is a self-consistent realization of the slow solar wind emerging from the coronal hole boundaries between the coronal hole and quiet sun. And we have investigated the energy injection process in these simulations and found that half of the solar wind energy is injected by the magnetic reconnection in this case. The left panel shows the magnetic field lines near the surface. So there are open field lines, which is connected to space. And also we have lower lying closed field lines. And the right two panels show the temperature and vertical flows black line shows the boundary between the open and closed regions. The magnetic reconnection between the closed and occurs between the closed and open field lines. And due to this magnetic reconnection, hot upflow appears inside the open regions, and which is connected to space. So some hot material is injected from the closed hot loops into the open, typically cool plasma. And you want to quantify the effect of this magnetic reconnection. We decompose the energy transport process. Especially the Poynting flux, magnetic energy flux in the solar atmosphere can be decomposed into the field aligned part, and the field crossing part. And in our estimation, about half of the total solar wind energy is transported along the magnetic field lines, but the other half is transported from the closed coronal lobes into the open field regions due to the magnetic reconnections. So in this sense, we think that both field aligned or turbulence-like or wave-like and the field crossing or reconnection-like processes are equally important in this simulation. And following this study, we are currently carrying out a parameter survey of this kind of simulations, especially focusing on the diversity of the solar wind characteristics. Typically, we know that the solar wind, there's two types of the solar wind. One is the slow solar wind, and the other is a fast solar wind. There are many categorizations exist, but one example is the speed of the solar wind. And on the speed of the solar wind, we know that we have a one-Shirley relations, which is an empirical relation between the solar wind speed and the magnetic flux tube expansion. For example, in the left figure shows the sun's global magnetic field structure. And near the polar regions, we have coronal holes, and the magnetic field does not expand horizontally. And fast solar wind is observed around here. And in the lower latitude, the magnetic field expands more greatly. And we typically observe the slow solar wind. And observationally, this is expressed as in the right figure. The horizontal axis of the right figure is the logarithm of the rate of the magnetic flux expansion. So expansion rate from the solar surface into the space. And the vertical axis is the speed of the solar wind. And we have a weak but robust anti-correlation between these two parameters. Physically, in the physical sense, what changes the speed of the solar wind? One is, of course, the expansion factor. This is very simple because the geometrical expansion of the magnetic flux tube leaves a weaker energy density, and it leads to the slower speed of the solar wind. If the expansion is small, then the energy is concentrated in a local space, and a faster solar wind will be produced. Other process is the height of the energy injection, energy dissipation, or energy or acceleration of the solar wind. This is also very simple because if we need to we accelerate the plasma from the lower height of the solar atmosphere, the plasma is very heavy and it is difficult to lift up. So the reproduced solar wind becomes slower. But if we can inject the energy into the higher atmosphere, mechanical energy into the higher atmosphere, then the the plasma material is very low mass, very light. So it is very easy to lift up, and faster solar wind is expected in this case. So the expansion of the magnetic flux and the height of the energy injection is those two are very important factor for the speed of the solar wind. And in order to check in our numerical simulation, we carried out a parameter survey of a four-dimensional parameter space. We have several parameters, mainly due to the local spatial domain of our simulations. So the numerical domain, boundary conditions, and the initial conditions are characterized by four parameters. One is the mean or average radial magnetic flux. And the second parameter is the strength of the small-scale dynamo, because the simulated convection zone is only a portion of the solar convection zone. The strength, realized magnetic field strength on the solar photosphere depends on the recurrent magnetic energy from the deep convection zone into the numerical domain, as found by the Matthias Rempel in the HAO. And the numerical domain is also a very important factor for the solar wind simulations. And we characterize the numerical domain in two parameters. One is the expansion rate of the horizontal domain, and the second one is the height of the expansion. So in total, 4-parameter space is surveyed in our study. But our numerical simulation is requires a large computational cost. So we decided to use the Latin hypercube sampling technique. It is very important to fill in the 4-dimensional or high-dimensional parameter space in a uniform way. If, for example, if we choose in the 2-dimensional case, if we choose only the actual component of the parameters, they are large unfilled space in this case. And in the middle panels, we can also parameterize in Monte Carlo or random ways, but it may produce overlaps along each axis. The Latin hypercube sampling avoids the overlaps in each axis, so it is an efficient way to fill the space without overlapping. In this study, we found a series of simulations with 16 parameter sets. So as a result, we have 16 numerical simulations in this study. This is a simulation results. There are 16 simulations in this only in this movie. So if you check very carefully, you may see the boundary between the different numerical simulation cases. And the left panel shows the radial speed so typically the speed of the solar wind. And the middle panel shows the mass density of the simulation. And the right panel shows the symbol indicates the VLOS, the line of sight velocity across this plane of the image. So it typically represents the transverse velocity of the alpha waves. And the wind speed ranges between the 200 to 600 kilometers per second. And also, when the solar wind speed is slow, we found a higher mass density. And if the solar wind speed is slow, then alpha waves seems to be weaker. So those are those characteristics are typically expected in the observations. So in order to check the parameter dependence on the of the solar wind properties on the, for example, the observable predictors. And this is a summary of the correlation between the solar wind predictors and the solar wind characteristics. The top panels show the solar wind speed, and the bottom panels show the solar wind density. And the left panel show the surface magnetic field, especially the surface average magnetic flux, total magnetic flux. And the next panels show the coronal brightness, which is measured by the STSW 193 intensity. And the right panel shows the rate of the expansion. And the rightmost panel shows the height of the expansion. Observationally, this rate of the expansion and height of the expansions are measured by typically the potential field extrapolations from the solar surface magnetic field or the global MHD simulations. And we have two numbers at the top of each panels. The R represents the Pearson's correlation coefficients, and the P represent the p-values. And among these plot, we found that the solar wind speed and solar wind density is well explained by the coronal brightness. The typical correlation coefficient is minus 0.71 and 0.91, respectively. Especially the speed of the solar wind anti-correlate with the coronal brightness. This is very natural because the coronal brightness, high coronal brightness means that there is a strong dynamo process near the solar surface. In the independent study, which is recently accepted in the APJ, we confirmed that the magnetically open corona can be bright if the small-scale dynamo is sufficiently strong. So if the corona is sufficiently bright and the small-scale dynamo is sufficiently strong, then the bright corona means the heavy, more dense corona. So it is very heavy, and it is difficult to lift up, so it leads to the slow solar wind speed. So this result is natural. And also, we have checked that the Wand-Shear relation. Wand-Shear relation is a weak anti-correlation between the solar wind speed and the rate of expansion. And sadly, we could not reproduce the Wand-Shear relation in this study. The correlation coefficient is rather positive, 0.339, and the p-value is large, 0.13. So there is almost no correlation between these parameters. So does it mean that the rate of the magnetic flux expansion is important? We don't think so. There will be possible reasons. One reason is that numerical dissipation is over-enhanced at the lower height, which leads to the slower solar wind and hides the component of the fast solar wind. Especially in the observations, we have a solar wind speed of 600 or 700 kilometers per second, but numerically we could not reproduce such fast solar wind speed. So that is a very important weak point of our simulations. And also, we have carried out insufficient number of simulations. We have only 16 simulations, but it is very the number of simulations is very small to fill in the four-dimensional parameter space. So of course, the number of simulations also matters. And also, there will be a bias in the magnetic field extrapolations, I guess. I personally speculate this because recently the open magnetic field flux problem has been discussed actively, and we guess that this is closely related to the validation of the magnetic field extrapolation models around the sun. And we have write a paper on these topics. So if you are interested in, please contact me or please check our papers. And the last point is what we think most interesting. The uniformity in the small scale dynamo is important for to reproduce the Wand-Shear relation. Let me explain. We think the small scale magnetic energy may regulate the diversity of the solar wind. The scale dependence of the magnetic energy determines the height of the energy dissipation, which determines the speed of the solar wind. For example, when the spatial scale or horizontal scale of the magnetic energy is small, then the reproduced coronal lobe is short, so the energy will dissipate at a lower height. And if the magnetic energy is distributed into the larger scales, then the coronal lobes will be longer, and the energy may dissipate at higher layers. So the spatial scale is very important, and the design of our experiment is like this. So typically we have a variation of the magnetic energy between the solar cycle maximum and solar cycle minimum, and we have only simulated only a rightmost part of the numerical simulations. And we assume that the large scale magnetic energy and the small scale magnetic energies are independent, and the small scale magnetic energy can be changed freely as an independent parameters. But in reality, in the observationally, it is not. Observationally, the large-scale magnetic field, magnetic energy varies in time, in typically in 11-year time scales. But in a shorter spatial scales, the magnetic energy is rather uniform, especially in the internetwork scale. Magnetic energy is very uniform in the solar surface. So this is the problem in our design of our numerical experiments. So please note that the small scale in this study is at about 10 megameter scale. So in other words, network scale or the supergranular scale. So we think that the uniformity in the small scale dynamo is required to reproduce the one Shirley relation. In other words, that So in other words, by changing the small scale dynamo strength in our experiments, we have drastically over enhanced change of the coronal brightness in the numerical simulations, and it hides the expansion factor dependence of the which is represented as a one Shelley law. But even in the real nature or real sun or real stars, we think that there will be possible locations where the one Shelley relation does not hold. A violation of the one Shelley relation will be a location where the large variation in small scale magnetic energy exists. Typically, near the active regions, near the sunspots, we have a very strong magnetic field. Horizontal is transported from the decaying active regions, and the small-scale magnetic energy is over-enhanced than the quiet sun or coronal holes. And also, if we compare the different stars, sun and the different sun-like stars, their small-scale magnetic energy may be different. So it's very dangerous to only rely on the one Shelley relation. And also, if we focus on the unsteady nature or the small-scale nature of the solar wind, the one Shelley relation will not hold. For example, this is the observations by the Parker Solar Probe. And this study report that there is a variation of the solar wind speed in the supergranular scales, which is also known as a solar wind microstrings. So in this shorter time period, the one Shelley relation does not hold, and dependence on the small scale dynamo, as shown in our study, will be very important to explain these variations. So this is a summary of my talk. We extended the established relative image model of the solar surface convection to simulate the solar wind with realistic energy input. And we found that the energy injection interchange magnetic reconnection seems to play important roles in energy input into the simulated solar wind. And we have recently carried out an extensive numerical parameter survey of the solar wind simulations to assess the reproducibility of the diverse solar wind characteristics. The simulated wind speed is well correlated with the coronal brightness, and we failed to reproduce the one Shelley relation, which implies that there exists a crucial role of the supergranular scale magnetic field in the solar wind diversity. So the solar wind seems to be very sensitive to the near-Sun magnetic structure than we have expected. And we think the radiative imagery simulations can be used as a unique tool to investigate the physical link between the Sun's small-scale magnetic activity and the interplanetary space environment. So thank you for listening.
Thank you. So, questions from the room as well as from online.
Mhm.
Yuhang?
Yes, hi. Thanks for the great simulation results. So I have a question about the setup of the numerical simulation domain. The width of the domain. How did you decide it? How does it expand with radius? I mean, is it determined based on your? It's not a flux surface. It's just. Is it just? How does your simulation domain expand with radius? How is it set up? It's greater than 1/r², right? I mean.
Yeah. For example.
The simulation, yeah. So this wedge, this little cone.
Yes.
So how do you? It's just expanding with. It's constant theta, constant phi boundaries. Is that right?
The horizontal boundary is periodic, and the top boundary is open, and the bottom boundary is also open in the convection zone.
Right. So basically, your simulation domain is limited to 1/r² expansion. It cannot be bigger than that.
Maybe I could not catch your points, but
I'm just saying that the simulation domain's width, the area, the cross section of the simulation domain, how does it expand? How does it increase with radius, distance? Is it?
I see.
Can it be bigger than 1/distance squared?
Yes. You mean this kind of?
Yes. So you can actually.
We define the super radial expansion factor in the numerical simulation box. And we use the Cope and Coulter's analytical expression of the super radial expansion. This is a bit detailed, so I haven't prepared a slide to explain that. But if you are interested in, please send me an email later. We define an analytical. We use the analytical expansion factor, and which has two parameters: the height of the expansion and the rate of the expansion, and which is surveyed in this study.
So your simulation domain can expand faster than 1/r². You do have that. I mean, the image I look is just like a 1/r². I mean, it can expand more than that, 1/r².
Yes.
Okay.
Yeah, we can expand you can use the super radial expansion.
Okay. Yeah, you do have that in the. Okay.
Yeah.
And also, sorry. So did you examine the Alfvén wave amplitude as a function of this height? Do you see that the Alfvén wave pressure? Did you examine that, whether it extend all the way beyond the sonic point?
I'm sorry. That is also what we needed to analyze, but currently we have a very poor analysis on the Alfvén wave amplitude or Alfvén wave characteristics. For example, the right panel shows the amplitude, and maybe we can produce the plot like the horizon, the height versus the Alfvén wave amplitude compared with, for example, the WKB or other numerical simulations. But the important weak point of our simulation is that we use the Alfvén wave. Yes, this fifth line semi-relativistic corrections, which is, in other words, the outbound wave reduction technique to speed up the computational computer simulations. So it reduces the effective outbound speed. So it is we need to be very careful when analyze the outbound waves in these simulations. But it is worth checking. Thank you very much.
Thank you.
Other questions from online, anyone? So I had a question on the same slide. If you bring that, Yuhang was asking.
You mean this slide?
No, that has the movie.
This one?
This one, yes. So, a live question: do these solar wind occasionally form vortex when they are expanding upward?
Sorry, what do you mean? Can I ask your questions again?
Somehow I don't know. Maybe I can't hear. So, can you hear me better now?
Yes, I can hear you.
Okay. So I was asking, when the solar wind is expanding, that cone, the left side, the cone type structure, are they forming like vortex type when they are expanding upward? Sometimes are they forming vortex?
Yeah, there is a vortex. For example, we cannot identify the vortex in this plot, but we have checked the horizontal slices at the height of the solar wind, and we have many vortex structures inside.
Okay.
And nature is rather torsional offband waves rather than the transverse offband waves.
Okay. Thank you.
Thank you.
Other questions? Michael?
Great presentation, great work. I'm not familiar with your model. How do you model the X-ray intensity?
In our simulations, of course, we assume the optically thin approximations, and numerically, we evaluated the differential emission measure in the numerical simulations. Then, in this case, the differential emission measure is directly used for the plot. And also, for example, in this figure, we use the AI193 filter, and we use the key anti-atomic database to mimic to convert the differential emission measure to the AI193.
Okay. Thank you.
Thank you.
Anyone else? Okay, if not, then let's thank our speaker again today for an excellent presentation. Thank
you very much.
You're welcome.